Assalamu alaikum warahmatullahi wabarakatuh. In this lecture tutorial, basically, we're going to discuss the second part of our inverse kinematics tutorial. We are going to discuss another example, which is basically I put for your midterm exam. So this you can consider as a solution of the midterm exam as well. And we will discuss further for this solution to see how to derive the inverse kinematic solution for that particular robotic problem. In the midterm, we just ask you to develop the forward kinematics relationship. So without further ado, let us start. So the robotic system was something like this. Let me draw it for you. So this was the base, and then there is a column, and then you have the first prismatic joint as follows. And then erase it. And then it's the second prismatic joint. And there is no prismatic joint, but there is a bend here. And then we have the wrist. With 2 degrees of freedom, basically revolute joint, and then finally is the tool point. Okay, so this was the system. So basically we had here a revolute joint as shown with the arrow, and then we have the prismatic joint, which is we define this as L2, which is a variable, and then L3, which is another variable, and this was theta 4, which is a variable as well, and theta 5, which is another variable. Okay, and these distance were given, which is constant d2, and then this was d3, and this was d4. Okay, first step is to assign the frames. So we can assign the frames with the different colors so that it is more clearer. So I choose this first Z0 as this, and X0, and then this is the Y0. Once you have the X0 and Z0, the Y0 can be used from the right hand rule. You can find out the Y0 as well. So your thumb is pointing, your thumb is pointing X0, index is pointing Y0, and middle finger is pointing the Z0. Then for this prismatic joint, this is the Z1. Sorry, I have to erase it. It's not in line. Okay. Z1. So X1 should be perpendicular to both Z0 and Z1, which is same direction as X0. And this is the Z2. We assume this Z2 in this direction. So X2 should be perpendicular to both Z2 and Z1. So it is in this direction, X2. Here, in this case, in our tutorial video, there was another prismatic joint, but here there is no prismatic joint. But to make the life simpler, I assume another frame here, though there is no joint, but there is a bend, so I can assume another frame. So I put here Z3, and X3 should be both perpendicular to Z2 and Z3. So this is X3, and Z4 is the revolute joint. So Z4 should be, if you use your right hand palm to find the Z4 direction, so it should be in this way, Z4, and X4 should be perpendicular to both Z3 and Z4, so which is, we can say this is the X4, and then Z5 also should be, if you use the right hand palm rule, Z5 should be in this direction, sorry, this is Z5, and X5 should be perpendicular to both Z4 and Z5, so this is X5, and finally Z6 can be same direction as Z5, but X6 cannot be same direction as X5 because X6 has to be perpendicular to both Z5 and Z6, so we put X6 in this direction. Okay, so this is basically the frame assignment. One way to check whether your frame assignment is correct is to match with this figure. So basically what you have to see that from two subsequent frames, whether it can be transformed as follows, that first it will rotate about Z0 so that the X0 and X1 is aligned, then it will shift along Z0 to make sure that they are in the same level, this D shift is there, and then it should move along X0 or X1 so that this A distance can be covered, and then it will rotate about X to make sure that Z's are aligned. So if you do this, you can do the transformation from 0 to 1, 1 to 2 like this, that means your frame of reference assignment is correct. So once you have this frame of reference, then you can calculate the you can develop the DH table. Let me write down the DH table. So basically, let's make a border here. So this is 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then 5 to 6. Okay, so 0 to 1 we have AI, alpha I, DI, and theta I. So this is the way to assign the A, alpha, D, and theta. So you can see that A1 is Z0 to Z1 along X1, so which is basically this value, which is A1 we define. Okay, so it should be A1, and then others should be 0, 0, 0, 0, but this one 5 to 6, if you see, it should be Z5 to Z6 along X6. So you can see here Z5 to Z6 along X6 is D4, but X6 is up, positive, D4 is going down, so it should be minus D4. Okay, then alpha should be 0 because Z0 to Z1 about X1, which is same direction, so it is 0, but others are 90 degree, as you can see, and this one should be 180 degree for Z3 to Z4 about X4. They are completely opposite direction, so it is 180 degree, and then it is 90 degree again, and then 0 degree. DI is basically X0 to X1, D1 is X0 to X1 about X0, which is nothing but 0 here. There is no shift about Z0 for X0 to X1. So this is 0, then it should be L2, then L3 minus L3 to be specific, and then it would be D2 minus D3, and finally it would be 0. For the case of theta is first two are zeros, and then minus 90 degree, and then 90 degree. Then we will have theta 4, but there is, even if theta 4 is 0, we will have a shift of 90 degrees, so it should be 90 degree plus theta 4, and then 90 degree plus theta 5, 90 degree plus theta 5. So this is the whole DH table for this robotic system. Now once you have the DH table, then you can calculate the homogeneous transformation matrix for A0, 1, 1, 2, 2, 3, and so on and so forth. So using this formula. So let us write down what are the individual transformation matrix first. A0, 1 would be equals to, by using this and using the DH table values, you can find out the value, the matrix values, individual components. It should be 1, 0, 0, A1, 0, 1, 0, 0, and then 0, 0, 1, 0, and then 0, 0, 0, 1. And your A12 should be 1, 0, 0, 0, 0, minus 1, 0, 0, minus 1, 0, 0, 1, 0, L2, 0, 0, 0, 1. Then we have A23, A23. We have to take the components from the third row of the DH table. So A23 would be 0, 0, minus 1, 0, minus 1, 0, 0, minus 1, 0, 0, and then 0, 1, 0, 1, 0, minus L3, then 0, 0, 0, 1. A34, similarly we can find, which is 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, minus 1, D2, and 0, 0, 0, 1. A45 similarly can be found, minus S4, 0, C4, 0, C4, 0, S4, 0, 0, 1, 0, 1, 0, minus D3, 0, 0, 1. A56, minus S5, minus C5, minus C5, C5, minus S5, 0, 0, 0, 0, 0, 0, 1, 0, then D4S 5 minus D4 C5, and then 0, 1. So you have now 1, 2, 3, 4, 5, 6 matrix. So your ultimate homogeneous transformation matrix A06 would be A01 times A12 times A23 times A34 times A45 times A56. So the result, you can just do the multiplication and can check the result. I have already done, so I will just directly write down the result. So here is the result. A06 is equals to, it's a big matrix. First column is C5 minus S4S5 minus S4S5, then C4S5, C4S5, and then 0, then minus S5, minus S4C5, minus S4C5, C4C5, C4C5, and then 0. And then here is 0 minus C4 minus S4, 0. And last column would be minus D4, C5, minus D3, minus D2 plus A1. And then L3 plus D4, S4, S5, S4, S5, then minus D4, C4, S5, C4, S5 plus L2, and then 1. So from here we can see obviously it is quite I think you already know that C5 stands for cos theta 5, S5 stands for sin theta 5, and so on and so forth. So from here we can see this term basically is the rotation matrix, and this term is the position vector. So we can separate them out in this form. The rotation matrix would be like this. C5 minus S5, 0, minus S4, S5, minus S4, C5, minus C4, C4, S5, C4, C5, minus S4, and position vector would be X, Y, and Z is equals to minus D4, C5, minus D3, minus D2 plus A1, then L3 plus D4, S4, S5, minus D4, C4, S5 plus L2. Okay, so if you try to solve this, we try to put some numerical values for the constants. So here the constants are, let's say A1 equals to, we put 5, and D2 equals to 3, and let's say D3 equals to D4 equals to 1. These are constant, as you know, from the robot structure. So this, during the design, we have already fixed it. So these are the constant values, just to make the equation simpler. So in this case, we can rewrite the whole thing for x, y, z. So your x, y, and z would be as follows: 1 minus C5 L3 for L3 plus S4 S5 S4 S5 L2 minus C4 S5 C4 S5. Okay. So now from here we can say that cos theta 5 equals to 1 minus x, cos theta 5 equals to 1 minus x. From here we can easily get the values of theta 5, and y equals to L3 plus S4 S5, and z equals to L2 minus C4 S5. So this equation, let's say we name it equation 2 and equation 3, and this is equation 1. So from equation 1 you can get the value of theta 5, but equation 2 and 3 you have how many variables? L3, L2, and S4, theta 4. So basically 3 variables, 2 equations. So you cannot, you have basically uh, more than one solution for this, because S5 can be easily calculated from the cos theta 5 as well. Sin theta 5 can be calculated. So, there are 2 ways to achieve it. You can either fix one variable, either L3, L2, or S4, or theta 4, and find the remaining 2 variables, or you can use the rotation matrix and define an orientation by defining the values of the rotation matrix, which whatever orientation you want, you can get it by assigning values to the individual component of the rotation matrix. So your rotation matrix, as you can see, what is the rotation matrix? Let me rewrite the rotation matrix. So rotation matrix here is basically C5 minus S5 0, and then minus S4 S5 minus S4 C5 minus C4 C4 S5 C4 C5 C5 minus S4. So now in this rotation matrix, values of theta 5 is fixed because you already got it from the inverse kinematic solution of x variable, x coordinate. So this equation 1 will give you the C5 value, S5 value in all these components. Only thing is the S4. So if you define each of the components, because S5, C5, these 2 components are already fixed, you cannot change, and these can be of your choice, and you define it to define a particular orientation of the tool point, and then from there what you can get is the value of theta 4. So once you, because you know these values, you know the S5, so you can get the value of theta 4. So once you have the values of theta 4, then basically you can get the value, and you can put this value here, and you can find out the values of L3 and L2. So this is the way you can solve it. So this is how basically all the inverse kinematic solutions can be obtained. So I hope this example was quite informative and useful for you to see how to, what is the procedure for solving the inverse kinematics for any robotic system. So hope you understood. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.